Hello, welcome to Econometrics. Today in this video, we will discuss that the fitted value xb in OLS regression is the projection of y on the column space of x, and the error term is orthogonal to x and the fitted value. So in our preceding video, we had seen that the linear relationship between the dependent and independent variables can be expressed as y is equal to xb plus e, and the OLS estimate of beta is x transpose x inverse x transpose y, and this beta helps minimize the sum of the square of the error. And we had seen that the immediate consequences of the OLS beta estimate gives rise to the orthogonality of independent variables and the error term. We also saw that the sum of the error, this is equal to 0, that is the error does not provide any unique information in the model. If the sum of the error is 0, it is obvious that the total of y, this is equal to the total of the fitted values. Here fitted value is represented by xb, and we can denote this xb as y cap. This is the fitted value of y, and from this relationship we can conclude that the mean of y, this is equal to the mean of the fitted value. And this also implies that the linear regression, it passes through the mean of the variables. Now let us move into today's topic. So the graph on the right, it represents the projection of y on the column space of x. So this is our hypothetical graph. If matrix x represented as the matrix of independent variables, if it has k columns, then the fitted value of y is the projection of y in this k-dimensional space, such that the error term is orthogonal to the fitted values of y. Matrix notation of linear regression equation, this is given by y is equal to xb plus e. Let us substitute the value of beta estimate. So this is equal to x transpose x inverse x transpose y plus e. Therefore e is equal to y minus x transpose x inverse x transpose y. So here this term, this is the projection. So let us write it is the projection matrix is given by x transpose x inverse x transpose. So this is equal to y minus py, and y here is in its post multiplication form. So let us take y common. Therefore, we are left with I minus p. Let us suppose I minus p is the error maker matrix. This is our error maker matrix my. So the residual of the error term, this is given by my, where m is our error maker matrix. And if we regress y on x, the error is e. So y is equal to projection of y plus the error term. So here projection matrix, this is given by x transpose x inverse x transpose, and m is the error maker matrix. So we have broken down y into two parts. The first is the deterministic part given by the projection of y on the column space of x, and the second is the error term. Now we are going to prove that both of them are idempotent matrix. So for idempotent matrix A, we have this property: A transpose is equal to A, and A transpose A, that is A square or simply AA, this would also be equal to A. So this is our projection matrix. Now let us take its transpose. For our simplicity, let me term it as A, B, C. So we know that A, B, C transpose, this is given by C transpose, B transpose, A transpose. And let us apply this property. First of all, C transpose. So the transpose of the transpose is the variable itself. B transpose, this is also X transpose X inverse, because A, B transpose is equal to B transpose, A transpose, and we get the same result. And we are left with A transpose. So this is X transpose, and this is again the same matrix, the projection matrix P. Therefore we saw that P transpose is equal to P. Now let us see whether the square of this matrix, projection matrix, is the matrix itself or not. So P transpose P, this can be written as PP, and let us write the value of P, that is X. Now let us multiply it with itself again. And if we compare this X transpose X with the X transpose X inverse. They are inverse to each other, so we get the identity matrix, and this is equivalent to multiplying by 1. So we are going to ignore this. So we are left with, this is again our projection matrix P. So we can say that P to the power n is equal to P. Therefore, the projection matrix is an idempotent matrix. Now let us prove that the error maker matrix, this is also an idempotent matrix. Let us see an example of identity matrix 1 0 0 1, and I transpose is also equal to I. This is equal to I minus P transpose, and let us operate it. This is I transpose minus P transpose. I transpose is equal to I minus P transpose is equal to P, because we have just proved this. This is again equal to the error matrix M. Now let us see I minus P. Let us expand it. I square, the identity matrix, the square of it is again the identity matrix, minus I into the projection matrix is projection matrix, plus is the projection matrix, it is idempotent matrix, the square of it is the matrix itself. The plus minus, if we cancel it, we are left with I minus P. So this is again our error maker matrix M. And if we iterate this process for n number of times, we get that M to the power n, this should be M. Therefore, both of the projection as well as the error maker matrix, they are idempotent matrix. Now let us see some of the interesting properties involving our projection matrix as well as the error maker matrix. What is the projection of y on x? This is obviously our fitted values. So if we post multiply the projection matrix by y, then we get this result, which is quite obvious. Now let us see what is the projection of x on x. So if we project x on x, so the result is x itself. If we post multiply this projection matrix by x, then x transpose x inverse and x transpose x, they will cancel out, and we are left with simply x. So what do we get if we project the error term on x? So is the x and the error term, they are orthogonal, so the result is 0. And if we post multiply the projection matrix by e, then we see that on the extreme right we need to multiply by e, and x transpose e here, this would be equal to 0. The independent variable and the error term, they are orthogonal. Now let us repeat the same process with a reference to our error maker matrix. First of all, what is the error when we regress y on x? What is the error? So this should be equal to the error, the residual or the error term. So what is the error when we regress x on x? So this is very obvious. Similarly, if we post multiply the error maker matrix by x, then we should get it as 0, because m is equal to I minus p, and this is equal to x minus, and px here it is x again, and so x minus x is equal to 0. So when we regress x with x, the beta term, it is 1 and there is no error. So this is its literal interpretation. So what is the error when we regress the error term with x? So is the error and x, they are orthogonal. So if we regress the error with x, the beta estimate, they are 0, and the entire residual term is the error term itself. So this is equal to e. And as we know, therefore m plus p, this is equal to I. And first of all, let us pre-multiply both the term by m. So and is m, that is the error maker matrix, it is idempotent matrix, so this is again equal to m plus mp, this is equal to m, and this expression is true only when mp is equal to 0, because mp on the left and mp on the right, they cancel out. Now let us pre-multiply both the sides by p. Again the projection matrix is an idempotent matrix, so this is equal to p. If we regress x on x, then we are not going to get any error. So if we regress the error term on x, so is the x and the error term are orthogonal, our beta estimate is 0, therefore the entire term is the error term. So in this case, the error term and the dependent variable, they are same, because y is equal to x b plus e, and if we regress x and e, they are orthogonal, so the value of beta is 0. So in this case, the dependent variable is the error term itself. And the sum of the projection matrix as well as the error maker matrix, this should be equal to identity matrix. And the product of the projection matrix and the error maker matrix, this is equal to 0. So this is a bit philosophical. We should always be alert that whether it is me committing the mistake or whether it is my mistake. So we have stated that y cap or xb or the fitted values, this is the projection of y on the column space of x, and we have also stated that the error term is orthogonal or perpendicular with each of the independent variable. And following the Pythagorean theorem, the square of the hypotenuse should be equal to the sum of the square of base as well as the perpendicular. And we have seen that while deriving the OLS estimate, the independent variable are orthogonal to the error term, so their dot product is equal to 0. So we have therefore y transpose y, that is the sum of the square of y, the dependent variable. This is, and if we operate it, if we expand it, and is the independent variable and the error term, they are orthogonal when beta is our OLS beta estimate, so they are 0, and we are left with and y transpose y is equal to, if xb, this is y cap, then beta transpose x transpose, this is given as y cap transpose plus e transpose e. In vector or matrix notation, this is equivalent to y square is equal to y cap square plus a square. And this is the golden principle for a balanced life. We should be always careful whether it is my error or whether it is me committing the error. E transpose E, that is the sum of the square of the errors. First of all, take whether it is my error, my transpose my, and is m, this is an idempotent matrix. We can write it as y transpose my. Let me write it here. This is again equal to y transpose my. This is equal to y transpose, and in place of this my we can write it as e. So this is one relationship, therefore. Otherwise, let me expand it again. So this is y transpose m transpose y, and in place of y transpose m transpose, this can be written as e transpose, because e is equal to my and its transpose is equal to y transpose m transpose, and we are left with y. Therefore, E transpose E is equal to either E transpose Y or Y transpose E. Now let us further expand it. So first of all, let us take E transpose E. This is equal to E transpose Y. And here let us take E transpose E. This is equal to Y transpose E. And this is equal to, in place of E, we can write it as Y minus Y cap. In place of E, I have written y minus y cap transpose y, and if we further operate it, this is equal to y transpose minus y cap transpose y. Therefore, E transpose E is equal to this result. Now let us again operate this. We have y transpose. In place of E, we are going to write it as y minus y cap. So we have seen that E transpose E is equal to this relationship from the Pythagorean theorem, and similarly we have proved these two relationships. Therefore, E transpose E, this is equal to. So if we compare these three relationships, so we can conclude that y cap transpose y cap, this can be written as y cap transpose simply y, otherwise y transpose y cap, which is quite obvious if we compare these three relationships. So this is the final result. Here P is our projection matrix and M is our error maker matrix. Px, how do we interpret it? The projection of x on x, so this should be equal to x. Py, this means the projection of y on x, so this should be equal to y cap, that is a fitted value. Mx, it means the error we are going to get when we regress x on x, so in that case we don't get any error. My, the error that we get when we regress y on x, so this is obviously the error term. Me, the error that we are going to get when we regress this e with x, so e and x, they are orthogonal, the beta estimates are 0. That is why the entire dependent variable is the residual itself. The projection matrix and the error maker matrix, the sum of them is equal to the identity matrix, and their product is equal to 0. This equation 1 is the result of the Pythagorean theorem, and second and third we have used the property that E is equal to my, and we have expanded it, replacing the value of E as y minus y cap, and E transpose E can be written as y transpose E or E transpose y. So these are some of the important findings that we have discussed in this tutorial. So this is it for this tutorial. Thank you very much for your time. Thank you very much, Econometrics Melody.